Good afternoon, all of you. I am Dr. Ramani Triari, Associate Professor in Chitara University. My paper ID is 6660. My paper name is Optimizing Fertilization through IoT, a smart approach for agriculture. This is my table of content, introduction, objective, proposed model, methods used, experimental evaluation and result analysis, conclusion. Introduction. Farming has always been an essential human activity that has sustainable civilization of thousands of years. With the rapid growth in population and the consequent demand of the food, it has become increasingly important to optimize farming practices to meet the records of the world's growing population. In recent years, technological advancement have revolutionized the way we approach the farming, leading to the emergence of a new approach known as smart farming. Actually, smart farming is an innovative approach to agriculture that nowadays that integrate technology into the farming practices, enabling farmers to optimize crop yield that reduces the waste and improve the efficiency. This approach uses a range of technologies, including sensor, drone, artificial intelligence, and the Internet of Things IoT, to collect the data and provide real-time insight into the crop health, soil quality, and other key indicators. Main objective of this paper is that we propose an IoT-based model focused on fertilization detecting, aiming to accurately predict the optimal quality and quantity of fertilization required for crops. The model operates through three key phases. First one is the data acquisition, second is the data transformation, third one is the data analysis. The model will contribute to sustainable agricultural practices and empowers with the tools to achieve enhanced productivity and profitability. Proposed model have three parameters. One is the data acquisition, and the next is the data transformation. Third one is the data analysis. Methods used in this paper is step one, data acquisition. In this step, data acquisition phase encompasses several vital operations, including deploying wireless sensor nodes, network configuration, and data collection. In the first step, selecting the area of cultivation. Subsequently, wireless sensor nodes are deployed in the field, configuring the network accordingly. Once deployed, the nodes in the field collect the data on primary nutrients. NPK abbreviation is the NPK, and the other external parameters such as temperature, moisture, and pH value. The collected data is then streamed and made available on the farmer's smartphone for access and monitoring. The soil samples are collected from various regional locations to normalize the NPK value. IoT-based wireless NPK sensors are embedded in the soil. Second method is the data transformation. The collected data is processed and transformed into the appropriate format to meet the application's requirement. This transformation ensures the data is compatible with the desired analysis or processing task. Additionally, the data is supplemented with additional inputs such as type of crop, frame, size, type frame, and any other relevant information. Once the data is appropriately formatted and enriched, it is migrated to a remote server or cloud platform for further analysis and processing. Third method is the data analysis. The farmer's request is processed at the cloud platform and the response is taken generated based on soil nutrient value and external parameter analysis. The analytic process considers the farmer's input and compares it with the collected data to provide relevant information and recommendations. Suppose for an example, a farmer query about the fertilizer requirement for a specific crop. In that case, the system analyzes the soil nutrient value. It provides a response that includes the recommended amount of fertilizer, composition guidelines, and suitable temperature condition for optimal crop growth. This response is returned to the farmer, enabling them to make informed decisions and take appropriate action in their agricultural practices. From these three phases, we have taken experimental evaluation that how you can experiment all these things. First step, data acquisition, step one. Choose the area of cultivation. Second step is the install and configure wireless sensor node in the selected area. In the third step, gather data using the deployed sensor nodes. And a table is maintained table acquisition phase data from the sensor. In this table, we have maintained nitrogen, phosphor, potassium, pH, and temperature. For individual, that means this is a formatted table where we can include the nitrogen value, phosphor value, potassium value, pH value according to the temperature. In the next step, the user determines crop selection time frame and the collected data organized and transferred to a cloud platform. Step 5, load the sample value or data into the memory. Set the algorithm parameters such as population size is 10, number of cluster taken k equal to 1, and maximum number of iterations 20, where I is taken to 112. Then next step, select the initial seed point that is taken as k, 15.949, 1.718, 13.068, 6.230. And next step, evaluate the objective function and update the solution. And in the next step, check the termination condition according to the condition. If it is met the condition, then stop the process. Otherwise, repeat the process till end. Then step 10, the step 10, obtain the optimal solution. For example, the optimal solution obtained after the 20th iteration is K1. Then the value is 4.634, 1.57, 4.715, 6.6, 29.30. The optimal value for the comparison 4.634, 1.57 and 4.715 already written in the previously 6.6, 29.30 are compared. This value is compared with the predefined database value for a wheat crop shown in the above table. Based on this comparison, the predicted amount of fertilizer NPK is 5366, 0.43 and 1.2. The variation is pH is 0.1. I have mentioned that one table where nitrogen, for potassium, pH value and temperature already maintained, and suitable temperature is 2.3 for this predicted fertilizer. Total, whatever the response we have found out, then this response is sent back to the farmer and suggesting implementing this type of fertilizer then to the cultivated area. This will helps the farmer to crop growth. Now, from the result analysis, we found that this type of crops have nitrogen value this much, for phosphorus, potassium value, pH value, and temperature. Like we have taken the example of hybrid rice, medium duration rice, corn grain, corn sweet, wheat common, winter wheat, soybean grain. For this type of crop, the nitrogen value is fixed, phosphorus value is there, potassium value is there, pH value and temperature value is there. Then from this part, then in this table makes a clear view that if we go for the fertilization, then we go for the knowledge. Farmers have the knowledge regarding the nitrogen, phosphorus, potassium, pH value, and temperature. According to this parameter, then one crop, any crop type may be growth or whatever the size and its temperature, pH value, it depends upon the fertilization growth. So farmers have the knowledge, a little bit knowledge regarding this. It will help for the further things. Then next we'll go for the conclusion part. Our paper, as our paper is a smart approach paper, then it gives the idea that how smartly farmers can go for the next step and crop, any type of crop can be growth according to the nitrogen value, potassium value, and appropriate value of the nitrogen, potassium, pH value, and temperature. Then we conclude that in this paper, conclusion is that this paper introduces an approach that utilizes IoT technology to create a model for fertilizer detection. The fertilizer, that means IoT technology nowadays is very emerging field, and it helps the farmer to detect any type of fertilizer which is helpful for the crop growth. The proposed model effectively addresses common fertilization challenges such as over-fertilization, under-fertilization, nutrient imbalance, all while ensuring cost effectiveness. Why our crop yield is not growth? Because if farmers given that over fertilization, then it hampers the crop growth. If it is under fertilization, then also it hampers the crop growth. Imbalance is there. So for that purpose, IoT technology help the farmers to the balance among the fertilization, which amount they can take in for the particular crop. So this technology helps the farmer for the crop growth. And it also cost effective. That means, and according to our technology, it also cost effective is there for the farmer. So this is one type of smart approach which is enabled for the farmer for the crop growth. And next, if you go for the further research, according to our paper, the further research will focus on incorporating additional external parameters. It also helps that if you go for the humidity, external parameter is also required for crop growth. First one is the humidity, weather condition to enhance the model's accuracy. Additionally, the cultivation area, where it is cultivated, which type of crop is required for that soil is also important. Will be divided into district of region and geographically based analysis to optimize crop quality and production further. This is all about our paper, which help for the farmer who has a little bit knowledge regarding the farming. Then, if this technology have applied to a particular cultivation area, then it will help for the crop growth and also helpful for the farmers' knowledge. Thank you.